All right, in this video, we're talking about stereochemistry, and in particular, we are now looking at how we can look at two molecules and explain their relationship. Now, previously, we looked at R and S chiral carbon centers, all right? So we were just focusing on how to label or identify R or S in a stereocenter. That's going to be really useful when we now start to look at relationships when we have two molecules we're looking at. So I'm going to give you a general graph of how to go through this process when you get two molecules. So the first thing you want to look at when you have two molecules and you're trying to determine their relationship, you want to ask yourself, do they have the same molecular formula? And if the answer is no, then they are not even isomers. If the answer is yes, we get to have more fun. They are isomers, and now we have more questions to ask. Do they have the same connectivity? Now, if they don't have the same connectivity, we know these are constitutional isomers. Constitutional isomers are connected differently. So if they don't have the same connectivity, then no, these are constitutional isomers. If they do have the same connectivity, then we would call these stereoisomers. Now the question is, are they non-superimposable mirror images of each other? Remember our hands, we've talked about our hands being chiral. They are mirror images. However, when I try to put one over top of the other, they are non-superimposable. If that's the case, this is where we get what's called enantiomers. So yes to that would give us enantiomers. And in this video, we're going to explore more about diastereomers. Let's first dive into enantiomers. Enantiomers are compounds that have at least one chiral center. Let's draw this alcohol here. Enantiomers would describe the relationship between two molecules. So here are enantiomers. They differ only by the stereocenter here. In this case, I have one stereocenter and it switches. So let's go ahead and practice that RS nomenclature. So let's label our number 4, which is back here. Okay, 4. The oxygen here will definitely be number 1, highest atomic number. And then between the ethyl and the methyl, remember that we have to look at what's bound next to it because right now the carbon and carbon tie. So the ethyl would win over the methyl. So this would be 2 and this would be 3. Now you can use your hand, or you can also see that if the hydrogen is back, it's going to be rotating to the right. The right hand there will give us an R. Let me write that in blue. So we have an R. And then if I switch it, you can go ahead and label this as an S. You can also practice this. So if everything on the molecule is the same, except for where in space that one stereocenter is, and it's R to S, these are enantiomers. Now, if a molecule has more than one stereocenter, let's say we had a molecule with multiple stereocenters, okay? There are 3 stereocenters and it was R, R, and S. And then each of them in the molecule that you were comparing it to switched, each of these stereocenters. So we had SSR, for example. These would also be enantiomers of each other. So for enantiomers, all stereocenters switch. All of the stereocenters switch. And like I said on the previous slide there, these are non-superimposable. Mirror images of each other. So here I have a model of the alcohol. We saw in my red little ball there is my OH group, and it's coming towards you, towards the camera there. In order for me to show you the enantiomer, all you would have to do is take this off and put it on the back side there. Okay, that's one way to tell when you're building a model that you do have an enantiomer, that in order to build it, you would have to take that off and put it spatially in a different spot. Okay, so another thing about enantiomers is that they have identical physical properties. They have the same melting point, boiling point, heat of formation, etc. There is a way that we can analyze these and figure out which one we do have, and I'll tell you at the end of this video here. Now, meso compounds are kind of special. They have chiral centers, but they are achiral. And you're like, what? Okay, what is going on now? Meso compounds look like enantiomers, and I'm going to show you how to identify them. They have a plane of symmetry. Okay, let's walk through an example here. Let's take this dichlorobutane structure. I have an S and an R here for my stereocenters. Now, if I were to draw the mirror image of this and say I was comparing these two structures, we would label this as an RS. So it looks like SR to RS. It looks like it would be an enantiomer, but it's not. Actually, there's this plane of symmetry right down the middle of the molecule. And this is because we have a methyl and a chlorine on both sides. These are actually the same molecule here. And I'm going to prove it to you by taking this compound and simply flipping it over. So all I'm going to do is take this left compound here, and I'm actually just going to rotate it. So I'm going to rotate this whole molecule on the paper. And when I redraw it, you'll see that I actually have our starting molecule I have on the left. So pause the video here and see if that makes sense to rotate the molecule 180 degrees. You're just rotating the molecule on the paper, and you'll see that it's actually the same. So meso compounds are these compounds that kind of look like enantiomers. Here we're going SR to RS, but there's a plane of symmetry. When you see the plane of symmetry, know that you have a meso compound. These are achiral. These are achiral compounds. Let's do one more example here. So what if I were to have something very similar? Instead of a methyl here, I have an ethyl, okay? And I'm comparing it to the following compound. If we walk through our R and S nomenclature, we would still get S, R, and this one would be R, S. So we're still going SR to RS. We're switching both of them. We think they're enantiomers, but we need to check and make sure there's not a plane of symmetry. Is there a plane of symmetry here? Well, there isn't. We have an ethyl group on this side and a methyl on this. So because of this, these are not meso. There is no plane of symmetry. And so these two compounds are, in fact, enantiomers. Both stereocenters switch. So let's write that out. These are enantiomers. simply adding that extra carbon to make the two stereocenters different, breaking the plane of symmetry, shows us these are enantiomers. These two compounds here are meso, and they are actually the same because we can rotate it and show that these are actually the same compound. Here I'm highlighting how in organic chemistry we can write things that look different, but they actually are the same thing. It's crazy. We're taking 3D molecules and trying to put them on a 2D piece of paper. That's why it's very important we understand these relationships. And that's why we've gone over Newman projections and cyclohexane chair flips and such, and molecular orbital theory. We understand these 2D drawings are actually depicting something 3D. Let's now move to our last piece of info for this stereoisomer, which is a diastereomer. Let's now go over diastereomers, and I'm going to draw us an example here. I'm going to use the same dichlorobutane structure. I'm going to draw the same dichloro structure I had on the previous slide when we were looking at enantiomers and meso compounds. And here we have an R and an S stereocenter. If you were given the second molecule here, and let's say only this stereocenter with that ethyl group was switched. And here we would have an SS. So we're going RS to SS. The only difference between these two, they're connected the same. There's only a spatial difference at one chiral center. So if you have an RS and we went to an SS, we're really only switching this one. Okay? These two compounds are not mirror images. This is what separates it from an enantiomer. Enantiomers can have more than one chiral center. As long as you switch all of the stereocenters, you get a mirror image, just like your hands, okay? If you don't switch all of the stereocenters, you end up getting what we call diastereomers. Let's talk about diastereomers. They have different physical and chemical properties. And some, but not all, of the stereocenters switch. You're probably like, wait a minute. Well, let's think about a compound that has an R-R stereocenter, okay? When you have two stereocenters, the number of possible diastereomers is 2 to the n, where n is equal to the number of chiral centers So if we had 2 times 2, that would be 4 possible diastereomers if you have 2 stereocenters. So let's just consider a molecule that has an R and an R stereocenter. And we're thinking about the same molecule, same connectivity here. R and R would be one possibility, RS, SR, and then you have SS. Now you're like, wait a minute, some of these are enantiomers, and you are correct, okay? Remember, we're dealing with relationships of molecules. So typically you're just looking at 2 molecules and deciding what their relationship is. These are terms we use to explain relationships, okay? And think about relationships you have in your life. You might be, well, a daughter or a son to someone, but you could also be a brother and a sister. You could also be a cousin or an uncle or an aunt. See how you can have actually more names to your relationships, right? The same is true with molecules here, but RR and R and SS, okay, these 2 are enantiomers of each other. And this RS, SR are enantiomers. Again, what you're going to be doing is just looking at 2 molecules and trying to figure out their relationship. If all of the stereocenters switch, RR to SS, those 2 are enantiomers. However, in red, I'm going to draw the diastereomeric relationships here. RR to RS, diastereomers, only one switched, okay? RR to SR, one switched, diastereomers, okay? Now see how we can do this with many of them. SR to SS, those two are diastereomers. And then the last but not least is RS to SS. See how relationships get kind of complicated? Well, don't worry, you're not going to be comparing a huge basket of molecules. You're typically going to be looking at two to explain the relationship. It is important, though, we understand that diastereomers, not all the stereocenters change. So first you're looking for if something is an enantiomer, and if it isn't, check to make sure if it's a meso compound, does it have a plane of symmetry? And then if not, look and see if it makes sense to call it a diastereomer. Now, so far we've just talked about carbon chiral centers. Now, technically any atom that can have 4 different groups bound to it can be a chiral center. Now, there are centers that don't stay chiral. And what do I mean by that? I mean that they racemize. And this is a term that just means that they can go back and forth between that R and S. Okay? Nitrogen centers that have 3 bonds to it can do this. And it's because this pesky lone pair. All right? So this lone pair here can actually invert. And this nitrogen inversion happens pretty quickly. Okay? We have this planar transition state that it goes through. So essentially you have this like tetrahedral type shape, and then it rotates into a transition state flat, and then it goes up. So this really makes it impossible to isolate a chiral amine. However, you can isolate a chiral ammonium, okay? Now, a nitrogen with 4 different things bound to it, no lone pair, 4 different things bound to it, can actually be isolated. We can do this by protonating this nitrogen here. So we have this lone pair, and if we protonate it, we'll end up getting this ammonium derivative. It's a nitrogen with a formal positive charge. This cannot interconvert, and so we can have nitrogen centers that are in fact chiral. Phosphorus can also do this as well. Now in this class, we're mainly going to be focusing on carbon chiral centers. The next topic I want to talk about is we've talked about enantiomers having the same physical properties. So how the heck did we even figure out that 2 molecules are enantiomers if they have the same physical properties? There has to be something different about them for us to even notice this difference. And there is. Enantiomers can rotate light, okay? Now, this is a topic about optically active or optically inactive. So I'm going to first talk about this technique using polarized light. Then I'm going to talk about it in the realm of reaction mixtures. And then I'm going to tell you how do you use the terms optically active and optically inactive, or not optically active, in your organic chemistry talk, okay? So when you do this technique, what you're going to be doing is taking a sample from your reaction, and you're going to be taking polarized light. So we have a polarizer here. We're taking polarized light. We've got our sample that we put right in this vessel. The polarized light is going through the sample, and we're observing what's coming out, okay? If no change occurs, the solution is considered to be optically inactive. Nothing changed with the polarized light. On the other hand, if you have a solution that is optically active, you'll put it in your polarimeter. You'll put the polarized light through, and your eye, okay, well, not really your eye, but the instrument will then see that the light is being rotated. Okay, the light is being rotated. This is literally the only difference between enantiomers, is that one rotates light one way and the other rotates it the opposite way. Okay, so if you have optically active solution that's in this pink vessel here, this would give you this rotation of this polarized light. Now, what does all this mean? So when you run this experiment, if your solution has 50% R and 50% S, okay, your R compound is going to rotate light a certain way, either right or left. One enantiomer is going to rotate the light clockwise, and we're going to call this dextrorotary. And it's given this symbol with a plus sign. The other enantiomer is going to rotate it opposite or counterclockwise, and this is called levorotary. These are older terms, but they're very important because if you have a mixture of a compound 50% R and 50% S, they're both going to rotate light exactly opposite. And if it's 50-50, That means that we're not going to see an overall rotation of light. One of the see, 50% is R, rotating it one way. R could rotate it clockwise or counterclockwise, but the other enantiomer, the S enantiomer, will rotate it exactly opposite. If you have 50 and 50% of both of your R and S, okay, you're going to cancel out any of the rotation of light. This is what we call a racemic mixture, okay? Racemic mixture means you have 50-50 of your enantiomers, okay? This will give you an optically inactive sample. Many times we're doing these reactions and we're actually forming a racemic mixture. We might form R, but we're also forming S, 50-50. This gives you a racemic mixture. We're going to be using this word quite a bit. Now, if you have more R or more S, we would call this an enantiomerically enriched sample, and this is described by the EE, okay? This EE is the percentage that is enantiomerically enriched in your sample. This will rotate the plane of polarized light, and that's because we know R and S are rotating it completely opposite of each other. If we have more of one, we're going to see the light rotate. We can analyze this amount of rotation to see how much of R or S is in our sample. So this is one of the techniques that we use to analyze enantiomers. Now, we have talked about diastereomers having different chemical and physical properties, and we can use this to our advantage. Because enantiomers don't have a difference in their physical properties, they're very hard to separate. In fact, you can't. There's no difference in polarity. There's no difference. They just rotate light differently. What we can do instead in the lab is we can kind of make a pseudo diastereomer. I'm telling you about this technique, but you won't be using this in this class in any of your exams. It's just a really cool technique that I wanted to show you. So enantiomers have identical physical properties and reactivity. And I say here in an achiral environment. Now this is typically what you have. You don't typically run reactions in chiral solvents or anything like that. Way too expensive. Most of the environments you're going to be dealing with are achiral. However, if you introduce a chirality, and this is what we're going to do. We're going to introduce tartaric acid in this example. Let me show you. We have two amines that are at this chiral center here, R and S. They would be impossible to separate unless in solution we make some kind of a complex. If we add tartaric acid, remember our acid-base chemistry. Here we have a carboxylic acid, okay? And here we have these amines. You can go through the pKa differences here and see that we're going to protonate our amine to an ammonium. We're going to deprotonate our carboxylic acid. These make these ionic bonds, and these complexes are actually diastereomers to each other. That's because if we look at the chiral centers here, we have an R and an S we're starting with. When they interact with this tartaric acid, they make this complex that has, in one case, an R, an R, an R. All right, so R, R, R. And this complex here is an SRR, SRR. The relationship between these two complexes are diastereomeric. That means that they have different chemical and physical properties, which actually allows us to separate them by recrystallization. So this is one of the ways that we can separate enantiomers is we just make them pseudo-diastereomers. This topic of enantiomeric resolution is actually really interesting and really cool. And it's important because there are times when we only want one enantiomer. So we've had to figure out ways to do this. So that's it for this video. We went through enantiomers, diastereomers, and those pesky meso compounds that look like enantiomers, but they're actually the same compound. Again, these are words we use to explain relationships between two molecules. And that's it for this video, and I will see you in the next video.